Dihedral group for an n greater than 3 is the set of all possible rigid motion of the n-gon that will cover that n-gon perfectly. By rigid motion, we mean the motion that don't change the shape of the n-gon. For dihedral group, the set elements are function of rotation and reflection. For example, think of a hexagon. The present image has no rotation, which is represented as 1. When we rotate it anticlockwise to 2 pi by n degree, it regains the previous shape but not pointwise. We identify it as R. In same manner, R2 up to Rn. At Rn, the n-gon returns to the initial place, so Rn equal 1. When we rotate it clockwise, the rotation is presented as R minus 1, which is equivalent as Rn minus 1. In case of reflection function S, think of an axis from vertex 1 to vertex 3. The n-gon is reflected with respect to the axis. After 2 reflection, the n-gon returned to the initial place, so R2 equal 1. If n is odd, the rotation is same. However, during reflection, the axis is drawn from one vertex to opposite edge. Like for pentagon, it is from vertex 1 to the middle of edge 3, 4. Group order. Imagine the vertex number from 1 to 5 for a pentagon. Now think on this pentagon. How many vertices can we index 1? All 5 of them? Let's take this one as 1. Now for 2. It must be consecutive to vertex 1. So we have 2 options. Now, after we place vertex 2, the other vertices places are fixed, which means there are 2 into 5 possible symmetries. So the order of a dihedral group is 2n. That's why we often write it as D₂ₙ. Another way can explain the order. Like we saw before, the n-gon requires n rotation to return to the initial position. In the same manner, each reflection has order 2. In total, 2n symmetries possible. For a pentagon, we take one reflection. Then there are the images of all possible rotations. Compare all of them. Each are different. So S is not equal to any Ri. We often write SR, RIS, or other combinations. Here, by SR, we mean S composition R. Here, we are going to see some properties of this group. First, for SR, S composition R, we first rotate it once, then reflect it once. Similarly, we do for SR2, SR3, SR4. For pentagon, we already saw each Ri is distinct from 0 to n-1. Here, we see SRI are also distinct. Therefore, the elements of the dihedral group can be written as Ri or SRI. Let's see for RS, one reflection, one rotation, and SR, one rotation, one reflection. We see RS is not equal SR, so this group is not abelian. Again, we do RS, one reflection, one rotation, and SR minus 1, one rotation clockwise, one reflection. They are same. Similarly, we can show RIS equal SR minus I. From the elements of the dihedral group, we see each can be uniquely represented as SK Ri, where k equals 0 and 1, I is from 0 to n-1. Even multiplication of 2 elements of this group can be represented as an element. For a pentagon, let's take 2 elements multiplication, SR2, SR1. This calculation outputs in R minus 1, which is same as R minus 1 plus 5. Through the n-gon, if we do 1 rotation, 1 reflection, 2 rotation, 1 reflection, we get the same result as R4. With this, we conclude our introduction to the dihedral group.